Okay, so we previously saw this idea that if I have a charged particle that's moving, it creates a magnetic field. And so it is kind of, it seems to say that a moving electric field, because any charged particle has an electric field, so a moving electric field creates a magnetic field. And a guy by the name of Michael Faraday, he realized that the opposite is true as well, that a moving magnetic field can create an electric field. And so that's where we get this idea of electromagnetic induction. So the premise is what Faraday discovered, that a moving magnetic field can create an electric field. And in fact, Faraday found out that there just has to be relative motion. As long as there's relative motion between a wire or a conducting material and a magnetic field, then there will be current induced in the wire. So if there is relative motion between a magnetic field and a wire, or just like a conductor, an electric field is created which causes current to flow in the conductor. And this idea, this is electromagnetic induction. This is causing electrons to move without there being necessarily like a voltage, like a chemical voltage that's causing that electric field. This is a different way of creating an electric field to make electrons move. So to understand kind of the nuances of like how much do the electrons move, like how big is that electric field, we need to understand a quantity called magnetic flux. Okay. So flux is a fancy way of saying like the amount that's flowing through. So magnetic flux is just the amount of magnetic field lines passing through a given area. Passing through. And so here's where we kind of have to quantify like area, this idea of like, well, what is it passing through? And just like when we saw with current create a magnetic field, you can have a magnetic field near a wire, but it wasn't very strong. We noticed that if we looped our wire, then we had a very strong magnetic field inside of our loop. So if I had just like a current running through here, the magnetic field I'd have next to, it's hard to see, the magnetic field that I would have like next to the wire, it'd be kind of weak, but if I looked at the magnetic field inside my loop of wire, I'd have a much stronger magnetic field. And so the same thing we're going to see with our electromagnetic induction. We see this effect happen more if we have a loop of wire. Okay, so we're going to talk about this idea of how much magnetic field is passing through this loop of wire, and we get into something called what's called an area vector. And so let me just kind of orient this idea of an area vector. We're looking at like how much magnetic field is passing through this. So if this is like representing my magnetic field lines, okay? So if my magnetic field lines, and they're going to the right here in this. And if I were to kind of put my loop here, we kind of think about how much is flowing through. If I kind of should, how much is flowing through my loop. And so definitely the magnetic flux depends on like, well, how many magnetic field lines do I have? So how many of these kind of like things are pushing out? How big is my loop? But it also depends on like the orientation of my loop, because if my loop is like dead on like this, I have a pretty big area that those magnetic field lines can go through. But if I switch my loop and I'm kind of orienting it like this, not as many field lines are going through. So you can kind of visualize not as many field lines go through. And actually there's a limit. If my loop is this way, then I have no magnetic field lines passing through my loop, okay? So we have to quantify something called an area vector. So if I were to kind of just show, like if these were my magnetic field lines here, And I'm just going to show different orientations of the loop. So if I had my loop like this, the area vector is actually pointing in this direction. And so when my area vector and my magnetic field are parallel to each other, then I maximize the amount of magnetic flux. Whereas if I oriented my loop like this, and my area vector was situated like this, now I have an angle, right? I have this angle between my magnetic field lines and my area vector. I'll put an A here. So I don't have as much magnetic flux. And then in the extreme is if I had my loop like this and my area vector was pointing down, I have no magnetic field lines passing through my loop of wire. Okay? So when we talk about the idea of magnetic flux, it's important to understand the area vector and what direction that area vector is oriented. Okay? So let's now kind of quantify magnetic flux. We symbolize it with the Greek letter phi. It's like a circle with a vertical line going through it. It's actually the lowercase of the two. The capital one looks like a capital I, and then the lowercase one is like this. Okay. So we're doing the lowercase phi. And our equation is magnetic flux is equal to B a cosine of theta, where B is our magnetic field. So the stronger the magnetic field, the more field lines I'm going to have, the bigger the flux is going to be. The A is our area vector, which should make sense. The bigger my area vector is, the more field lines can pass through that area. And then the theta is the angle between A and B. So when theta is equal to 0 degrees, I maximize the flux. And when theta is equal to 90 degrees, you minimize the flux. It's actually 0. The units, magnetic field is measured in Teslas. So Teslas times area is meters squared. It's actually a unit called a Weber, WB. So magnetic flux is measured in Webers. And oftentimes we don't necessarily utilize or just find out pure what is the magnetic flux, but we use the idea that if the magnetic flux is changing for a conductor, then I'm going to have an induced current. Okay? So with this idea of magnetic flux, we get into the bigger idea of something called the induced EMF. Okay? So induced EMF specifically is the voltage that is induced in a conductor when it is in the presence of a changing magnetic flux. So it's a specific type of a voltage, a specific type of potential difference that we can create without having chemicals. So normally, when we did circuits and that kind of stuff, we said that we have a potential difference, and we just said that potential difference came from a battery or a power supply, but we never really quantified how does a power supply, how do I plug something into an outlet, how does it have that difference of 120 volts? And so you can either have that voltage difference due to a chemical potential difference because of a reaction between the anode and the cathode, and there's a different rate of one losing their electrons, the other, and we have a difference in charge. You can have a chemical potential difference. And the other way you can have it is you can have a potential difference that's created because of an induced EMF. Okay? So our symbol for this, because it's a very specific type of voltage, we symbolize it with the Greek letter epsilon. And we saw this with EMF when we had our power supplies and we looked at the idea of terminal voltage of a battery. So it's EMF It's still going to be, I'm going to do the units first. It's still going to be volts, because it's still a voltage that is being created that's going to cause electrons to flow. And in terms of the equation's a little bit more complicated, so I'm going to come over here on my board. The equation for induced EMF is that epsilon is equal to negative n times change in magnetic flux over change in time. And you're like, oh, that doesn't look so complicated. But remember, there is an equation for there's an equation for flux. So let's go through that. This kind of expands out. N is the number of turns in my loop. So in the case of this example, when I just have like one loop, the n value would be 1. If instead I made a second loop, my n value would be 2. If instead I made a third loop, my n value would be 3. So it's how many times is that wire looped around in that given area. And the negative, we are going to talk in the next lecture or next video. We understand the idea of the negative with something called Lenz's law, and that tells us a thing about direction. Negatives usually tell us about direction. But let's kind of expand this out in terms of the flux. So induced EMF is equal to negative n, and remember, flux is BA cosine of theta over delta t. And I've taught you that anytime there's a delta in physics, in calculus, it's actually a derivative. And so if you look at this, this is the derivative of BA cosine theta with respect to time. There's 3 terms in here. So technically, if you're taking the derivative of a product, you'd have to apply the product rule. And so the product rule means you would just take the derivative of the one variable multiplied by the constants of the other. And so this can actually expand out into a larger equation of, so let's do it if my flux is, my magnetic field's changing. So this would be A cosine of theta delta B over delta T plus B cosine of theta delta A over delta T plus B A delta cosine theta over delta T. Okay, so this is just the product rule applied to my equation for magnetic flux. And so just kind of the examples that we are going to be exposed to, we're going to really only have one of our variables changing in time. So it would be like our magnetic field is changing, our area is changing, or our orientation is changing. But this would be if the magnetic field is changing, because if only the magnetic field is changing, then my change in area would be 0, and my change in orientation would be 0, and these terms would just go away, okay? This is if the area vector is changing. So something is changing about the size of my loop, and this would be that the orientation of the area vector is changing. So again, for the level of physics we are doing, you are not going to have like 2 things change at one time. Like it's just going to be one factor that's changing. And if it's only one factor that's changing, we just focus in on the one that is changing, and the rest are going to go to 0. Okay, so let's just kind of think about this again. If only my area is changing, if somehow my area of my loop changes, then there is no change in magnetic field. So this whole term becomes 0. And there is no change in orientation, so this whole term becomes 0. So it just simplifies to become this middle term. If my magnetic field is changing, these 2 become 0. Okay. So I think it's pretty straightforward, but you're going to be like, we'll definitely do some more examples, or just do examples of how you can have one of these factors changing. But what I want to do in the next video is kind of go over what does this negative mean in terms of direction of the electric field and how the electrons are going to be moving in my conductor.